Right. Hi guys. Another video as part of the Electromagnetics 344 course. So something that I want to look at now is called the critical angle. So what is the critical angle for when we look at obliquely incident waves on dielectric media? So over here I have region 1, over here I have region 2. I have some electric field in this case. This field is incident on an oblique angle, right? So theta I is bigger than 0, and it's also perpendicularly polarized. So, but you can do the exact same thing for a parallelly polarized case where EI just lies in the plane of incidence, which, given this setup, is the XZ plane. So what is going to happen? Let's look at the physics. So if I have a case where the relative permittivity of this part, right, of this medium is bigger than that of this medium, epsilon R2. So I've got a denser medium over here than here. So I'm moving, for example, from something like glass to air, away on an oblique incident angle. And this angle becomes bigger and bigger and bigger, right? What happens then is this angle, this theta t, the transmitted field, well, that angle is also going to become bigger and bigger and bigger. So as this field, let's use 2 pens, see if we can do it like that. So if this angle is going to, let's move my setup in here, right? So if this angle increases, then so will this angle. It'll increase, up to some point at this angle where this reflected field is, essentially this angle, this transmitted angle is pi over 2, 90 degrees, right? Where this transmitted field, is running along the interface. And if I increase it even more, well, then I'll have, obviously, as we talked about in class, total reflection. So nothing goes through. We obviously want to find out what is this value of theta I. So what is this value of theta I that causes the transmitted field, this angle, to be pi over 2? And it is super easy to figure that out. Because we know from the boundary conditions, if you look at the previous, one of the previous videos that I made, I know, or you can use Snell's law of refraction. I know that beta 1 x sine theta I is equal to beta 2 x sine theta t, right? Or alternatively, I can also write this as sine theta t is equal to sine theta I, which is just equal to this. But beta is my phase constant, right? And I'm working with a lossless case over here. That is assuming no losses. Alpha is equal to 0. So what is beta then? Beta is just very simply then E1 over omega, which is the radial frequency, mu 0, epsilon 2, right? And this is just permeability of free space. Why am I using permeability of free space? Because I'm assuming non-magnetic material. Okay, and essentially I need to write this out a bit more. I could have sorry about the epsilon r1 over omega mu 0 epsilon r2. That is the full expression for now the permeabilities and the permittivities. That all cancels out. Lovely. And I'm left with this, which is also equal to the index of reflection, right? The index of reflection, that also tells us something about the properties of the media. That's just equal to the square root of epsilon r. Ooh, that's not right. That's epsilon r1 over here. 1. Oh, let's cross it out. Sorry about that. That's a 1 and that's a 2. Now, the critical angle is, as I said, theta I is equal to c. So critical angle is theta I equals to theta c, such that theta t, the transmitted Now the transmitted angle over here, theta t, is equal to pi over 2, so that my wave comes in there. The transmitted wave lies exactly on that interface between the two media, so theta t equals to pi over 2. Alright, well, I can just substitute that in this equation. So sine pi over 2, which is equal to 1, right, divided by sine theta c is equal to square root of epsilon r1 over epsilon r2. So this gives me that theta c is equal to the inverse sine or arc sine of epsilon r2 over epsilon r1. Or if I express this using my indices of refraction, n2 over n1. And that's it. This is how I can calculate the angle, the critical angle at which the transmitted angle of my transmitted field is equal to pi over 2, when that angle will cause a reflection along that interface. Anything more than this angle will cause what we call total reflection. Okay, awesome. So that's it. That's the critical angle.